Hello everyone and welcome to this lecture related to Pharmaceutical Technology 2 module. So let's get started. Just quickly to remind you that in the previous lecture I already introduced pharmaceutical emulsions and mentioned some reasons for developing emulsions in the pharmaceutical field, routes of administration for emulsions, principal components of emulsions, and theories of emulsification. So all these topics are covered in the previous lecture. Now this slide will show you the general classification of emulsions. Generally speaking, we have two types of emulsions: oil and water emulsions. In this kind of emulsions, we have the oleaginous phase as internal phase and the aqueous phase as the external phase. And we have water and oil emulsions. So in this case, the emulsions having the aqueous phase as the internal phase and the organic phase as the external phase. Now this slide will show you some notes related to emulsions. So the first note is that the viscosity of emulsions depends on their constituents. So it might differ greatly depending on the constituents. So sometimes we have emulsions in the liquid state, other times we have emulsions in the semi-solid phase or state. So this is related to the viscosity. The second point or note, I'd like to mention that liquid emulsions can be used orally, topically, or sometimes parenterally. So that's the second note. While semi-solid emulsions normally used as topically, as topical dosage forms, and examples of these emulsions are creams. Creams are emulsions in the semi-solid dosage forms or semi-solid state. The fourth note, emulsions include certain lotions, liniments, creams, and others. So sometimes we can give another name to emulsions, like creams, for example. Creams are a type of emulsion, but the structure of these creams are actually emulsions because we have internal phase, external phase, and emulsifying agent. This slide is showing you the tests used for the identification of emulsion type. So we have three methods for the identification process: miscibility test, conductivity measurement, or staining tests. So imagine we have an emulsion and we don't know what is the type of the emulsion, if it's oil in water or water in oil. So what we are going for the identification is using one of these tests. For the miscibility test, in this case we are using water or oil to see the miscibility of the emulsion with the water or the oil. If it is miscible with the oil, it's oil and water emulsion. If it is miscible with the oil, then we have water and oil emulsion. For the conductivity measurement, if the emulsion is conducting the electrical current, then it's oil and water emulsion. If it is not, then it is water and oil emulsion. So it's very simple depending on the conductivity of the electrical current. For the staining, we are using water soluble and oil soluble dyes, and we will see which phase is going to take the dye, and according to this we will identify the type of the emulsion. This table is showing how the different tests are working. So the miscibility test, so in case of oil and water emulsions, and in case of water and oil emulsions. So please read this table carefully because it's very important for the identification of the different types of emulsions. Now, as I mentioned previously, that an important component of the emulsions is the emulsifying agents. So the emulgent or the emulsifying agent should have certain properties. Like for example, it should be capable to promote emulsification and maintain the stability of the emulsion for the intended shelf life of the product, compatibility with the other ingredients, not interfere with the stability or efficacy of the therapeutic agent or agents, stable and not deteriorate in the preparation, non-toxic, and it should possess little odor, taste, and color. So these are the general properties of the emulsifying agent. Now this slide is showing the different types of emulsifiers. We have different types according to the structure of the emulsifying agent. These include carbohydrates, protein substances, high molecular weight alcohol or alcohols, surfactants, and clays. So these are the different types of emulsifying agent with examples. So please read the different examples related to the emulsifying agents. Now this slide is showing the emulsifying agents. The first type is Acacia. So Acacia is dried gummy exudate obtained from the stems and the branches of Acacia senegal or the other related species. So sometimes the excipient can be called in a different names like Acacia gum, Arabic gum, E414, and so on. It's very complex chemical compound, loose aggregates of sugars, hemicelluloses with high molecular weight, approximately 240,000 to 580,000 Daltons. So these are general information about Acacia as an excipient. It can be used as emulsifying agent, stabilizing agent, suspending agent, binder, viscosity increasing agents. So these are some information about Acacia as emulsifying agent. This slide is showing the structure of Acacia. As you can see here, that we have the structure of Acacia. So we have a protein core, that's the chain up, and then we have a polysaccharide fraction. So the polysaccharide fraction comprises approximately 95 to 99% of the structure, while the protein core is only 1 to 5% of the structure. And also there is another table, so in which the concentration of Acacia according to the use of this excipient. Like for example, if we want to use it as emulsifying agent, we should use a concentration of 10 to 20% and so on. So these are some information about the structure of Acacia and the use with the concentration of this excipient. This slide is showing the properties of Acacia. It's important to know the properties of the excipients used in the formulation of different pharmaceutical formulations, like the acidity or alkalinity, the pH of 5%. Acacia weight per volume aqueous solution is 4.5 to 5. The hygroscopicity of this excipient, solubility is important as well, and specific gravity, the viscosity of the solution of Acacia. So all these information are important for us if we want to use any excipient in the formulation process. So please have a look and see what kind of properties Acacia has and how these properties are affecting the final formulation. One last thing we need to mention here regarding the Acacia is the safety. So, is it safe to use Acacia in the pharmaceutical formulations? The answer, yes. It can be used in cosmetics, foods, and oral and topical pharmaceutical formulations. So, it's generally considered as non-toxic material. And sometimes we have some reports related to the hypersensitivity to this ingredient. This is general information for Acacia. So hypersensitivity can occur to any kind of material. Sometimes the body is reacting with any type of material. So this is something general. The other example related to the emulsifying agents is Tragacanth. So this is another carbohydrate type of emulsifying agent. So Tragacanth is a natural emulsifying agent obtained from the dried gum from Astragalus gummifier and the other related species. It has different synonyms. The gum is actually consisting of a mixture of water insoluble and water soluble polysaccharides, and the molecular weight is 840,000 Daltons, and the functional category of this emulsifying agent, so it can be used as emulsifying agent, suspending agent, or viscosity increasing agent. This slide is showing the structure of Tragacanth. As you can see here in the slide, the emulsifying agent, or this excipient generally, is consisting from two separate units. So we have the structure is actually not a single structure. Is a mixture of two units: the arabino-galactan unit, which is unit A, and the tragacanthic acid unit, which is the structure B. So it's not a single structure, but it's actually composed of two structures together as a gummy material. So this structure is not required from you to keep it like in mind. So just to let you know that this structure is composed from two units separated, and these the arabino-galactan unit and the tragacanthic acid units. This slide is showing the properties of Tragacanth. So please have a look and notice the most important properties, like the acidity and the alkalinity of the aqueous dispersion of Tragacanth, the moisture content as well of Tragacanth, if it is hygroscopic or not, the solubility, specific gravity, the viscosity as well of Tragacanthic dispersions, and the safety of this excipient. So please have a look and read all this information. The third example related to the emulsifying agents is gelatin. Gelatin is a protein type emulsifying agent. So gelatin is a generic term for a mixture of purified protein fractions obtained either by partial acid hydrolysis, which is type A gelatin, or by partial alkaline hydrolysis, which is type B gelatin. These types of gelatins are obtained from the partial hydrolysis of animal collagen obtained from cattle and pig bone, cattle skin, pig skin, and fish skin. So all these are the sources for gelatin. Gelatin may be also a mixture of both types, means type A and type B. So we have either type A or type B, or sometimes mixture of them. The names for this excipient are quite different. So E441, gelatin, collatin, and so on. So these are the different names for these excipients. The protein fractions consist almost entirely of amino acid joined together by amide linkages to form linear polymers having a molecular weight ranging from 20,000 to 200,000 Daltons. This excipient has functions of emulsifying agents, coating agent, film forming agent, gelling agent, suspending agent, tablet binder, and viscosity increasing agent. So it has a variety of pharmaceutical applications like emulsifying agents and so on. So these are some information about gelatin as excipient. This slide is showing the structure of gelatin. So just have a look, and as you can see here, the protein type of structure, we have the amide linkages that separate the different portions of the structure forming gelatin. So just have a look for this structure. This slide is showing the properties of gelatin. So generally speaking, like we normally start with the acidity and alkalinity of the aqueous solution of gelatin. So for example, the 1% aqueous solution having a pH of 3.8 to 5.5, type A, while the alkaline type having a different pH. So here, as you can see, that using different grades or different types of gelatin will make different solutions regarding the pH. So that's why it's important for us to know exactly what type or what grade of excipients we are using in the formulation. Also, the density is important. So the density is 1.32 gram per cubic centimeters. For type A, also the density is different for type B solution. So every type of gelatin having a different density. The moisture content is 9 to 11. The solubility, here's some information about the solubility and how the excipient is behaving inside water. So and generally this excipient is considered as a non-toxic and non-irritant material. This slide is showing the viscosity of gelatin solution. So as you can see here, the different concentrations of gelatin having different viscosities, and also the viscosity is changing according to the source of gelatin. So as you can see here, the solution of 6.67% of aqueous solution of gelatin having different viscosities with the different sources of gelatin, and if you increase the concentration to 12.5, the viscosity will increase, but again the source of gelatin is very affecting the viscosity and the concentration as well. This slide is showing another category of emulsifying agents. So here we have the sorbitan esters, so sorbitan fatty acid esters. So we call these kind of emulsifying agents as spans. So this is the slide showing the structure of the spans with the different substitutions that give the different grades of spans. So spans is a surfactant kind of emulsifying agents that is normally used as emulsifying agents for making water in oil emulsifiers. This type is working for promoting the emulsification of water in oil emulsions. So that's some information about the spans. So this slide is showing the trade names of the different grades of spans. Like for example, we have sorbitan monolaurate, which is a span 20 in this case. Monooleate, sorbitan monooleate, this is span 80. Monopalmitate, span 40. Monostearate, this is span 60. So these are the most important grades of spans. So each type according to the structure and then the span grade, either 40, 60, 80, 20, so depending on that. The functional category of this type of excipients, they are working as dispersing agents, emulsifying agents, non-ionic surfactants, solubilizing agents, suspending agents, and wetting agents. So they have a different functions in the pharmaceutical formulations, but most importantly, they are used as emulsifying agents related to emulsions, and they are normally used for the emulsification of water in oil emulsions. This slide is showing the uses of spans, sorbitan or sorbitan esters. So they are normally used as emulsifying agents, so used alone in water in oil emulsions. So here the concentration is used from 1 to 15%. In combination with hydrophilic emulsifiers in oil and water emulsions, normally used in a concentration of 1 to 10%. Used to increase the water holding properties of ointments, also we are using 1 to 10%. Solubilizing agents using the same concentration, and then wetting agents normally for insoluble active constituents in lipophilic bases. In this case we are using 0.1 to 3% as a concentration of spans. This slide is showing the appearance of different spans. So we have different grades of spans, and everyone has different appearance. So in this case, sorbitan monoisostearate having yellow viscous liquid, monolaurate same, but if we go to monopalmitate, it will be cream solid, and so on. So each type of sorbitan may be having different appearance or different color. Now the second table is showing the properties of the different spans. So the acid value of each span, the density, the HLB value, the hydroxyl value, the iodine value, and the melting point. So I'd like you to have a look, what do we mean by the acid value, what do we mean by the hydroxyl value, and what do we mean by the iodine number. So these are important information you need to mention. You need to have a look and know what do we mean by these terms. This slide is showing the last type of emulsifying agents as an example. So here we have the polyoxyethylene sorbitan fatty acid esters, or what we call them tweens. So we want to know what are tweens, what are their properties, what are their pharmaceutical applications, and are they safe to be used in the pharmaceutical formulations or not. So we'll try to answer all these questions in the next slides. So on this slide we have tweens. So as you can see here, the tweens in the structure, we have the sorbitan moiety, and then there is a fatty acid moiety connected to the right side of the structure, and then the polyoxyethylene moieties attached to the sorbitan to the left side. So the structure of tweens, generally speaking, is composed from 3 portions. The first is the sorbitan structure, which is the ring, and then to the right side we have the fatty acid structure attached to the structure of the sorbitan, and then we have the polyethylene oxide units attached to the sorbitan as well from the left side. So the structure is composed of three major components, and these the different grades of twins are differing according to the fatty acid moiety attached to the sorbitan and the number of the polyoxyethylene units attached to the sorbitan. So the sorbitan is the same, but the difference is in the fatty acid moiety attached to the sorbitan and the number of ethylene oxide attached to the sorbitan moiety as well. According to this, we will get different grades of twins, or the other name for twins is polysorbates. So we have, for example, the polysorbate or the twin 20, 40, 60, 65, 80, 85. This is according to the to the fatty acid moiety and the number of ethylene oxides attached to the sorbitan structure. This slide is showing the two tables. The first table is the molecular formula and the molecular weight of the different polysorbates or twins. So twin 80 or polysorbate 20 having the molecular formula of C58, H114 and O26. The molecular weight is 1128 and so on. So each grade of twin having a molecular formula and molecular weight. And the second table is showing the chemical name of the different twins or polysorbate. Like for example, polysorbate 20 is polyoxyethylene 20 sorbitan monolaurate. So that's the general description of the chemical name of the different twins or polysorbates. Now this slide is showing the pharmaceutical applications of different twins. So it can be used as emulsifying agents for oil and water emulsions in a concentration of 1 to 15%, in combination with another emulsifiers for oil and water emulsions from 1 to 10. Used to increase the water holding properties of ointment from 1 to 10%, solubilizing agent from 1 to 15, and also wetting agents from 0.1 to 3%. So it's approximately the same concentration as the twins. But here, one important thing I'd like to mention is related to the use of twins. So twins are hydrophilic surfactants. So they are most likely used in the fabrication or the emulsification of oil and water emulsions, while spans, they are normally used for the fabrication of water and oil emulsions. Now I have two questions mentioned in this slide. The first question, which class of surfactants twins are belonging to? So as you know, that surfactants can be classified into ionic and non-ionic. So the ionic could be cationic, anionic, zwitterionic, but we don't know what kind of what type of surfactants twins are belonging to. So this is something you need to have a look. And also what are the critical micelle concentration of different twins. So I'd like you to have a look and find the critical micelle concentration of twin 20, twin 80. So these are the two concentrations, the two twins you need to find the critical micelle concentration for twins. So this is type of homework. I will mention it later on Google Classroom. In this slide, I try to give some information about the physical properties of twins. So generally speaking, polysorbates or twins having different colors at 25 degrees centigrade depending on the grade. Like for example, twin 20 having yellow oily liquid, while if we are moving to twin 65, it's tan solid in appearance. For twin 80, it's yellow oily liquid, and polysorbate 120 it's yellow liquid. So it depends on the grade. The structure is different and the appearance is also different according to the nature of chemical nature of twins. Now the composition or for the different twins, also we have a variety in the structure. Sometimes we have a problem with fatty acids because it's difficult to get a purified form of each fatty acid. So if we are talking about twin 20 or polysulfate 20, we'll see that the major fatty acid in this case is telluric acid, so it's from 40 to 60%. But it's not the only fatty acid. We still have some of the caproic acid, palmitic acid, and so on. But we are depending on the fatty acid that's mostly existing in the structure of the twin. For polysorbate 40, we have more than 92% of palmitic acid. For polysorbate 60, we have from 40 to 60% of stearic acid, and for polysorbate 80 we have more than or approximately 58% of oleic acid. So according to the fatty acid, that's the major fatty acid that's attached to the sorbitan, we are classifying the different types of or different grades of twins. Now the third table is showing the HLB value for the different twins. So because they are differing in their structure, what we are expecting to see is the different HLB value, hydrophilic lipophilic balance value for the different twins. Like for example, for polysorbate 20 we have 16.7. If we are moving to polysorbate 80 is 15, and then polysorbate 120 is 14.9. So these types of surfactants, they are hydrophilic surfactants having high hydrophilic lipophilic balance values. Also, the specific gravity at 25 degrees centigrade is differ from one emulsifying agent to another. So for example 1.1 for polysorbate 20, and then we will have 1.08 for polysorbate 80, and so on. Same is for the viscosity, because they are different in the structure, so what we are expecting different viscosities for different twins, as mentioned here in this slide. Now in this slide we are continuing with the physical properties of different twins. So the first table is showing the solubility of different twins in the different solvents. Like for example, if we are talking about polysorbate 20, so it's soluble in ethanol, it's insoluble in mineral oil, it's insoluble in vegetable oil, it's also soluble in water. So that's an example, and the same for the different grades of twins. Also the second table is showing the acid value and the hydroxyl value, the moisture content and the saponification value for the different twins. So you have to know some information. What do we mean by the acid value, hydroxyl value, and the saponification value of what do we mean by these terms? So this is homework. Different twins having different acid values, as you can see here in this table, and also different hydroxyl value and saponification value, and also the moisture content is different. The surface tension is also at 20 degrees centigrade is different for the different twins. So we have, like for example, for twin 40 is 41.5, for polysorbate 80 is 42.5. So they are slightly different in case of surface tension. So what does that mean? If they have different surface tension and different structure, different physical properties, they are most likely working as emulsifying agents by different not different ways, but different potency or different concentrations or you need more or less from this surfactant to promote the emulsification process. So these are the general properties of twins, generally. This slide is showing the safety of twins. So an important question we need to ask if the twins are safe to be incorporated in the pharmaceutical formulations or no. So the WHO has set an estimated acceptable daily intake for tweens like 20, 40, 60, 65 and 80 calculated as total polysorbate ester at up to 25 milligram per kilogram body weight. So this is the limit. The maximum limit is 25 milligram per kg body weight. Polysorbate 20 has moderate toxicity by intraperitoneal and IV routes of administration, moderate toxicity by ingestion, and it's a human skin irritant. So that's some information about the toxicity of twin 20. The LD50 for hamster oral is 18 gram per kg, while that the LD50 in mouse by IV route is 1.42 grams per kg, and the LD50 in rat by oral route is 37 grams per kg. So these are some information about the toxicity of tweens using the different routes of administration. As you can see here, the different tweens have different toxicities, and the concentrations, acceptable concentration, the maximum acceptable concentrations are also depending on the type of the tween and the route of administration. In this case, the oral is different from the IV, and also the model or the animal use having different toxicities as well. This slide is showing the toxicity of polysorbate or twin 80. So it's moderately toxic by IV route, mildly toxic by ingestion. It causes eye irritation. So it has some effects. It might be carcinogenic, and it has some reproductive effects on human beings. So these are some information about twin 80. This is one of the commonly used excipients in the pharmaceutical formulation, so just keep these in mind. The LD50, using the different routes and the different models, like for example the mouse, the rats. So as you can see here, intraperitoneal, using intraperitoneal route in mouse, the LD50 is 7.6 grams per kg, while using the IV here the toxicity, the LD50 is 4.5 grams per kg. If we are moving to the oral route of administration, the concentration is 25 grams per kg. So according to the route of administration, we have different limits for the toxicity. So what are the factors that affecting the toxicity? Is the type of the excipient, type of tween, route of administration, and the model or the animal used for the study. Like for example, is not the same. Like as you can see here, the LD50 for mouse by intraperitoneal is 7.6, while in case that's in the mouse, but in case of the rat is 6.8. So as the toxicity is different for the different animals used in the study. Okay, and also so we have the type of the tween, we have the route of administration, and the type of the model used for this study. Now the last thing related to the tweens is the incompatibilities of tweens. These, as I mentioned in the previous slide, that tweens are one of the most commonly used excipients in the pharmaceutical formulation. So they have some incompatibilities. So the first incompatibility is that the antimicrobial activity of paraben preservatives is reduced in the presence of polysorbates. So why this is happening? Because polysorbates are surfactants, so they are forming micelles, and if the antimicrobial preservative trapped inside inside the micelles is no longer acting or promoting its activity as antimicrobial preservative. So that's one of the incompatibilities happening during the pharmaceutical formulations. So in which, if we are using tweens or any kind of surfactants, if the concentration used is within the critical micelle concentration or higher than that, so there is a probability that the preservative or even the other component of the formulation will be trapped inside the micelles, and this will create some kind of incompatibility inside the formulation. So finally, we have the stability of tweens and their storage. Um, Generally speaking, the oleic acid esters are sensitive to oxidation. So tweens sometimes are sensitive to oxidation. So it's important not to leave tweens exposed to air. So this will promote the oxidation process and cause hydrolysis because of the oxidation of the tweens. Polysorbates are hygroscopic and should be examined for the water content prior to use and dried if necessary. That's another important thing. Prolonged storage can lead to formation of peroxides, so this is another thing we need to consider. And the last thing, polysorbate should be stored in a well closed containers, protected from light, in a cool and dry place. So all this information give an indication how stable the polysorbates or the tweens, and how we can storage them to be in the correct condition before incorporating them inside the formulation. So at the end of this lecture, I'd like to summarize the topics covered in this lecture. So the lecture is covering the classification, the general classification of emulsions, and then we move to the identification, the methods that's normally used in the differentiation or the identification of different types of emulsions. So these are we mentioned the general methods, but if we want to characterize the emulsions, we can use different characterization techniques for the emulsions. But we mentioned the staining and the conductivity and the miscibility tests for the identification of water in oil and oil in water emulsions. And we moved later on to talk about the most important part in the emulsion, which is the emulsifying agents or emulsifying agents, the classification of these emulsifying agents and the different types of them. And I already covered different types of emulsifying agents, moving from the carbohydrates type, Acacia and the Tragacanth, moving then to the carbohydrate to the protein types of emulsifying agents like the gelatin, and then we move to the surfactants. In this case, we talked about the spans and the tweens. So I hope that I managed to cover all the topics titled in this lecture. So please read this information, and if you have any questions, let me know. My email and the other information, the contact information, are mentioned in the next slide. So please enjoy reading this lecture, and I'll see you in the next lectures. See you.